Okay, back with another video on the cigar box tube amp, for lack of a better description. I've done a bit of work. I figured I wouldn't make every little incremental videos along the way. I'd wait to get some substantial work on it finished before making another one. So here I am. I've got the transformers mounted in the positions that I think they're going to work best with respect to interference with each other. Decided to put the tubes up front. Let me just tilt this thing up. So the vacuum tubes are going to be up front right here. You know, you want to see them. The tube amp, you want to see the tubes. I think they should be up front first and foremost, highly visible. You'll always want to see the glow, certainly. So they are up front together. Got the switch mounted. I decided to put the switch on the very front. So this is our key operated on-off switch. This is a very quirky amp. I've never built anything like this before. So got the feet on. I think I had a video on that. And the level control, the volume control knob, I decided to put it back here as opposed to a knob on the front. The only thing I wanted on front was the key. I think I want to change this knob to black. I think that might look better, but again, this is another cabinet knob that I had on hand, attempting to stick with the budget, having to use things I have on hand. Decided to use another, drill the hole into a cabinet knob and put it over the potentiometer that's mounted under here, and just burned a little notch into it right there with the soldering tip of the soldering iron, and have a little screw here. This hole was a mistake. When I was originally going to mount both transformers next to each other here, that hole was going to be for the other transformer. So I utilized it with a brass screw to sort of be our indication of zero volume. And this was intentional, a design feature to put the volume back here, because it really kind of forces the user to interact more with the amp, to actually have to reach over and kind of hover over the amp briefly to turn the volume up and down. It's just sort of it really forces you to get more involved, I think, as opposed to just reaching for a knob on the front. And plus, this is kind of a quirky amp, and I wanted things to be different from what's traditional for these kinds of amps. I want it to be oddball, and I want it to be a bit inconvenient. That's the nature of this. It's kind of got an old feel to it. The back of the amp, I've mounted my really cheap, inexpensive and cheap speaker binding posts, but they work. They accept banana plugs and they accept wire. Little tiny holes in there. It wouldn't fit anything substantial. If you had fatter speaker wire, you'd have to wind it around there and then tighten it down. And I found a power cord in my box of junk. So I drilled the hole, put the cord through here. This is a little bit of glue from a glue gun holding it in there. They didn't want to put a grommet in. This is actually a thick piece of wood right here, and I don't have any grommets that would fit that, and don't need one anyway, because this is not a metal enclosure that's going to chew away at the power cord. Now, looking inside, this is kind of convenient. When you flip open the top, they rest on the transformers. This is our volume control potentiometer. It is a double ganged audio taper. This is the bottom of the tube sockets. Of course, the transformer wires. I do have, you can see here, I do have the output transformers soldered to the speaker binding posts. But I do need to switch around a couple of wires here, and I'll just splice them and do an inline splice, because I have a feeling that I chose the wrong output tap, and I'm going to cover that in another video. So the power cord comes in. I tied a little knot right there for strain relief in case the glue breaks. And I'm starting the process of going through the schematic and tracing, building paths or connections one by one. So I've built the path from our 117 hot in through the fuse to the switch. That's a little switch up there. I've moved it up here, and then that's as far as I've gotten. And then here it is right here. This is the neutral wire. I haven't done anything with that yet. So the hot wire comes in and attaches. Let me see if I can move this. Attaches to the fuse on one side, goes to the fuse, then goes to the switch here, and then from the switch I just have it resting on the board right now, because I'm waiting for the next connection is going to be my diode, my rectifier diode. I don't have that in yet in the mail, so that's just waiting there. Alright, one interesting point, and I was kind of thinking, why am I even making these videos, you know, besides to document this, maybe something I'll go back and watch one day. I'm not sure if I ever watch it, but in describing what I'm doing here, I got to thinking who my audience might be, if anybody ever, for this video. And I figured, well, I doubt anyone who's a seasoned amp builder, someone who's been doing this forever, is going to want to watch someone else build an amp. So I figured the people that might be interested in this video are those who are new to the hobby or just starting out. So what I'll do along the way is provide little descriptions of what I'm doing, little pointers, things you learn the hard way over the years. And I'd provide little pointers here and there as we go for each portion of the build here. So that's what I'm going to do right now. And I'm going to start with something that's important with respect to the power, the line voltage, in terms of how to hook it up. And let's see. What I'm going to start with here, because that's what I've done already. So I figured I'd describe, which of these lines. There's two cords coming into this one. There's not a third prong on this one because it's not earth grounded. I didn't need an earth ground in this case because I have a wood chassis, and there's really nothing to earth ground. And so this is a plus in keeping with the original schematic, and that's what I kind of wanted to do, is in keeping with the original schematic, it was a two-pronged cord, not a three. So for those reasons, I'm going with the two-prong. Now you can't, when you have one of these two-prong cords, you'll notice, at least for the modern cords, and I'd recommend using a modern two-prong cord, you'll notice that one prong is bigger than the other. this one here is larger than that one there, and that's designed that way intentionally to fit into outlets in only one direction. You ever get it wrong, you got to flip it over. And the reason for that is one of these blades, I don't know what you call them, but one of these blades is hot and the other is grounded or neutral, I don't know what you call it. But so one of these is actually, if you were to touch the wires themselves, one of these is relatively safe if you touched it, because it's referenced to earth ground back at the panel box, and the other one is hot. That's the one that's going to shock you. And for that reason, oh, and I can tell you that the smaller of the two blades is the hot one, and the larger of the two is the grounded one, the safe one. So for that reason, when you have two wires coming into your amp, you just can't randomly pick which one you want to use to switch and to fuse. You want to switch, again, I don't know if you can see it, my switch is right here. You want to switch and fuse the hot wire, the dangerous wire. And then the earth grounded or the grounded wire will become your ground for the circuit. So what you can do is just, with a cord, find the smaller of the two, the smaller of the two prongs or blades here, and just trace it on this side, trace it all the way back in. You could use a continuity tester also on your voltmeter. Trace it all the way back into your amp, and then that's the one, and that's the one you want to hook up to your fuse and your switch, which is what I've done. And that's why I did that first, so I wouldn't forget. Okay, so that's one pointer there. Another way, well, no, I won't get into that. Okay. Now, the next thing I wanted to do, at least cover in this video, is the transformers. I should have bench tested these transformers before I mounted them, but I didn't. Well, I tested for open circuits and shorts, but I didn't test for turns ratio. Now this might get into more detail than someone's interested in, but that's really what the focus is going to be for the remainder of this video, or this installment, is turns ratio of the transformers. And probably the best way to do that first is to show you on paper. Now what I'm doing is I'm testing the transformers, and then I'm going to the side, because I close this down. I decided, because of the size of this thing and the lack of real estate, that this would look too cluttered with taps back here for 2 ohms, 4 ohms, 8 ohms, and 16 ohms. I like to keep these binding posts, you know, spaced apart to a good degree, in case someone wants to wind wires around it and close it up. There's little chance of a short. So I wanted to pick the output of the transformer, the output line that's going to be best suited for this particular vacuum tube. And yeah, the transformers say right on them, they actually have some indicator here that for the output side, black is 0, so that's, you know, black is going to go to black back here. But for the other wires coming out of the secondary of the transformer, white is 2 ohms, green 4, yellow 8, and so on. You really can't trust that stuff, especially these things are inexpensive. Chinese transformers. Not that there's anything wrong with Chinese stuff, but it's like anything, regardless of where it comes from. If it's inexpensive, I tend to trust it a little less. And this came from I don't know what source this is. I trust some of the bigger sources, like Hammond and some other many other companies that make good transformers. But I didn't spend hundreds of dollars on these transformers. I spent $30 each, which is, believe me, inexpensive for output transformers. So I'm not going to trust them. I'm going to verify which tap to use. I want a tap that's suitable for an 8 ohm load. And I'm going to describe how you figure that out. And it's really easy. It's very little math. It's just a multiplication. But to figure this out, one needs to know a little bit about transformers and what they do and how they do it. So I'm going to actually measure. I'm going to measure these things, these transformers, and figure out which tap is the best one to use. But before I do that, it's probably better to show on paper what I'm doing first. And this is probably a good procedure to do regardless of where the transformers come from, just to verify that that we do have the correct turns ratio. And it really is kind of simple. It's not anything highly mathematical. It's just conceptual. So I'm going to show on paper first what I'm going to be doing, and then I'm going to show you how I'm going to do it with the voltmeter, the oscilloscope, and the signal generator. Basic lab test equipment. So let me hit pause here and get set up with some paper and show you what I'm going to do. Okay, first a transformer. And what I'm showing here is the vacuum tube, and the vacuum tube is going to be driving the transformer. A transformer has a primary winding and then a secondary winding. And the primary winding is hooked up to the vacuum tube, and the secondary windings have taps for 4, 8, and 16 ohms, for example. Could be different configurations. And that's where we would eventually hook the speaker to, between the 0 and the 8 if it's an 8 ohm speaker, or between the 0 and the 4 if it's a 4 ohm speaker. Now, the key here is transformers don't, their windings, if you were to put your digital voltmeter across the primary to measure resistance, you would get a very low value of, for example, 50 ohms or something like that. If you were to take that, if you were to put the ohm meter across, for example, the 0 to 4 ohm tap, you would get a very low resistance, like less than an ohm maybe, or maybe a couple of ohms, something like that. That's meaningless. It's meaningless for our purposes. What a transformer is doing is it's reflecting impedance. So this tube wants to see a certain impedance. It's not resistance, it's called impedance. It wants to see a certain impedance, and we know what it wants to see from the tube data sheet generally. And I'm looking to see if I have that handy. In this case, a typical operation, for example, wants to see a load resistance of 3,000 ohms with this tube that we're using. So I know, given that data sheet, that this tube wants to see 3K or 3,000 ohms. That's what it wants to see from there forward. So if we were to hook an 8 ohm speaker, directly across the tube, well, first of all, the tube would not be able to source the current. An 8 ohm speaker needs a lot of current. wouldn't be able to source it, and there would be an imbalance, a major imbalance between the resistance of the tube and that of the speaker, and we would get little, if any, power transferred to the speaker. So what we need to do is, we've got our 8 ohm speaker here, but our tube wants to see 3 kilo ohms. So the purpose of this transformer is to, we use the word reflect, to reflect this 8 ohm output, or this 8 ohm speaker impedance, back to the tube such that it appears to be 3K. And it does it by a process of, a tube will put out a, how do I draw this, a high voltage but a low current. And what the transformer does is it takes this high voltage and the low current and it flips everything around. So the transformer will reduce the voltage but increase the current. Remember, our speaker needs a lot of current. So it does it with the magic of the turns ratio. Turns, just what it says. There's a winding in the primary with a whole bunch of turns, and then there's the windings in the secondary with fewer turns. So there's a turns ratio, and it's the ratio of the number of primary turns to the number of secondary. And, oh, now I'm doing this from memory here, but it's been a while. Now, I'll get it right. So, let me cut to the chase here. The impedance that is going to be seen, I'm going to call it, I don't know what to call it, Z primary, let me call it, is going to be equal to the I'm going to call the turns ratio N, the turns ratio squared multiplied by the speaker impedance, in this case 8 ohms. So we talked about reflecting the impedance. So you can see if the turns ratio is high, and let's just say the turns ratio is 10, so 10 to 1, we would square that times 8, right? And then that would be 10 squared is 100 times 8, so that would be 800 ohms. So with a turns ratio of 10, even though we have an 8 ohm speaker, the plate of the tube would see 800 ohms. Now in this case, in my case, I want to see 3K. So, you know, what kind of turns ratio would I need for 3K? Well, given an 8 ohm speaker, I'm designing here for an 8 ohm. Well, you know, you could just do this by trial and error, or you could rearrange the equation to figure out the turns ratio. So we know that we want Z primary. We want to see 3K. It's a different equation here. And we know we have an 8 ohm speaker, so I'd bring the 8 down here. And we know that the turns ratio squared, so we would take the square root of that and get rid of the square over there, and so that would be, and I can't certainly do anything like that in my head. Let me see if my cheap, everything I have is cheap. Let me see if my calculator can do this. So 3,000 divided by 8, square root 19.4. So turns ratio should be in the area of 19. For this tube, that's what I need. I'm looking for a turns ratio around 19. Now, knowing that, now that I know that, I want to measure these actual transformers to find out what kind of turns ratios I have. Now again, they already, they come, there's one more thing I want to say, but they come from the factory saying right here, this is a 3K ohm transformer. But for what tap? Well, there's, I'm getting some more details here, but let me just cut to the chase and say I don't trust it. So I want to measure the turns ratio and see really what's going on here. Doesn't say for what tap, and there's 4 taps on this thing. My transformer has a 2 ohm, 4, 8, and 16. So I'm going to measure all these taps right here and figure out which one of these is closest to the 19 turns ratio of 19 that we need, and that's the one I want to connect to the speaker binding posts. Whew. Can't believe I got through that without screwing something up. Maybe I did. Okay, so let's go ahead and measure that. You hit pause here and get my bench set up. So what we're, oh, you know what? The way we're going to measure it is simply, let me draw the transformer again. I was going to draw a single. That's a horrible transformer. So I'm going to put a signal. I'm going to use a 1K hertz signal into the primary, and I'm going to measure the voltage, and I'm going to also measure the voltage across the secondary, and that ratio will be the same as the turn, that ratio will be the same as the turns ratio. So if we have 10-to-1 turns ratio, and we were to put in 10 volts, we should get out 1 volt. Now if we don't know the turns ratio, that's where we put in a certain voltage and see what we get out, and that'll tell us what our ratio is. Now there's one more thing, just in case if anyone's watching who really knows what they're doing. Well, I'm not that good at this, but I'll say this. I'm using the wrong transformer. Before we get into measuring these turns ratios, let me just divert for no more than a couple of minutes. I'm using the wrong transformer here. There's a single-ended, draw a tube again. Okay, this amplifier is in a single-ended configuration, and I'm using a push-pull transformer. So the transformer I'm using actually looks like this. Primary, secondary. And the difference is, I'll make this brief, a push-pull transformer is designed for idling DC currents to run in these 2 different directions like that. And the way the core is designed, the laminations in the core, it's designed, these DC currents cancel out the magnetic flux at idle in the transformer core. Whereas in a single-ended arrangement, when this amp is idling, no signal, there's going to be a constant amount of direct current running through that core. Now, if that could go along with if the transformer. So let me back up. That could saturate the transformer and cause it to behave in bad ways. So single-ended transformers are designed specifically to handle and deal with this constant amount of DC current that's not being canceled out in the same way it would be with a push-pull. I'm using a push-pull, but I'm only using one side of it. I did that for a couple of reasons. One, because I've never done it before and I want to see what happens. That's why I do this stuff, partially. Learning experience. But also, I could not find a single-ended transformer that fit within my budget. I found a couple for $150 a pair, but that would leave me $50 left over for all the other parts, and I couldn't do that. And I found some old used ones for 70, 80 bucks a pair, but they didn't have cases and shields on them. They were kind of exposed, and they looked ratty and horrible, and I didn't want that either. I wanted something that was enclosed. So I ended up with these, and I figured I'd try them out. And because this is such a low power amplifier with a pretty low idling current, I think it's gonna the quiescent current maybe somewhere around 40 milliamps, maybe 20. I'm not sure. I gotta plot a load line on this thing. That's something for a future video. I think I'll do that. I'll try to plot a load line. If I remember how. My God. Okay. So, but I think that these transformers, because it's such a low power amplifier, I think the push-pull will be able to handle it without saturating. But we're going to find out. And if push comes to shove and I have to buy a couple of single-ended transformers, I will. But I'll have learned something, and that's why I'm doing it. Alright, so on to the measurements. We're going to measure the turns ratio of the transformers to find the best output tap of the transformer to use to drive an 8 ohm load. I hope I'm not in for any surprises here. Jeez. Alright, I'm going to hit pause. Alright, got my test set up. So what we're going to be looking at here is on the primary windings, I have my signal generator, and I'm going to be measuring voltage. There's the signal generator, and I've got them hooked to the primary windings, and I'm measuring voltage with the digital voltmeter. Right now I've got 7.6. Okay, so primary, secondary, and in the secondary we have different colors. So we've got yellow, white, green, turns ratio in, and orange. So right now I'm hooked to the white. So I have, on the primary side, I've got, with a 1 kilohertz tone, I've got 7.6. So white, 7.6. On the secondary, my voltage RMS is right there. It's 389 millivolts. So that's 0.389. So the turns ratio is going to be 7.6 divided by 0.389, which, let me do that, 7.6 divided by 0.389, 19.5. That's pretty close. 19.5. What did I say? I think that's what Well, I'll go look later. I think it's what I said was going to be right, just right. So, got that lucky. Let me switch the oscilloscope over to the green wire. Output tap on the secondary. And let's see what we got. Again, we maintain 7.6. Green 7.6. Now on the output we have 545 millivolts. 0.545. Let me run that. 7.6 volts divided by 0.545. 13.9. So that's too low. Okay, let me switch the oscope over to the orange tap, orange line from the secondary, and we still maintain 7.6. And for an output voltage, we now have 1.093. 1.1. Wow, that's going to be low, isn't it? 7.6 divided by 1.1, it's going to be 7. 7.6 divided by 1.1 is 6.9. So that's a turns ratio of 7. That's crazy. Couldn't use that. And last but not least, there is a yellow tap, which is the one that was allegedly for 8 ohms. Okay, I'm in the yellow. 7.6, and our output is 768 millivolts. 0.768. So 7.6 divided by 0.768 is equal to 9.910. So it looks like our white tap is going to be the best. Now what I want to do is, again, trust but verify, is knowing that the white tap is going to be the best. Let me test the second transformer to make sure that white tap is consistent with the first. Now, I don't know what the white, I don't know what my transformer sheet is, but it was supposed to be yellow for 8 ohms, according to the transformer, but yellow is, that can't be. Yellow is a turns ratio of 10, and that would reflect impedance back, an 8 ohm load back, by 10 squared is 100, times 8 of course is 800. So that would reflect it back as 800, but I need 3K. So to reflect 3K, 19.5, let me see what that gets us. So 19.5 squared, there's no square button, times 19.5 equals, times our 8 ohms, that's 3K. We need the white tap. Unfortunately, these are the mistakes one makes when building these things, especially when I haven't done it in a while. I've already soldered the yellow wire to the output terminal, so I'm going to have to switch that around to the white one. That's an easy fix. That's a bummer. All right, well that's how we do it. Let me put this down and test and hook up the other transformer and see if the white one is consistent with this one. Okay, I'm now hooked up to the other output transformer onto the white wire, and we have 7.6 to the primary, and we have 389 millivolts to the secondary, which unbelievably I mean, I can't believe it, but that's the same 389. That's identical. That's an accident. I mean, it's great. They're so perfectly wound, but that white is exactly matched between both transformers. That would never happen again. It wouldn't be that good, but so white it is. White provides us with the turns ratio we need to reflect back 8 ohms as 3K, which the tube wants to see. So there you have it. I hope I did that right. I'm sure. Yeah, it's just been a while. Trying to remember this. This is easy stuff to remember, though. It gets a little hairier when I start doing load lines. There's a big difference when you start doing load lines between a resistive load and an inductive load. And I always have to remember that. It gets kind of weird when you have an inductive load, which is what you have with a transformer. But anyway, so that's great. We figured out. So I'm going to have to desolder, clip a couple of these wires, and make sure that the white one goes to the output. The white wire from the secondary goes to the positive wire of the terminal block. The speaker terminals. I'm thinking ahead here. So I'm going to do that, and then I think the only other thing I'm going to do this morning is wire up the find the schematic here. I think I want to wire the heaters, the filaments right here, or the tubes, and then it would be really cool just to get them glowing. You know, just turn the tubes on and see them glow a little bit to make sure that, well, I know they work. I put them in the tube tester. So even if I put this amp down and never come back to it, at least I have a hand warmer or something. So I think I'm going to wire those filaments today. Plus I've never... These are R10. Okay, yeah, I think I'll do that and then call it a day. And maybe paint that knob, that volume knob black. I think I like black better. Might look better with this. So, but there you have it. That's where I am so far on the cigar box tube amp. What if I can do, since I'm looking at the output, I don't know if it's fair if I could do a frequency sweep and see what the frequency response is of the transformer, but yeah, I'm going to wait and see. I'm going to be surprised later. That's 2K. Let me go down to 100 hertz. Okay, we're now at 216 hertz. 170, 90, 80, 30. That's pretty good. It's a good frequency response. Nothing funny happened. Let me go up to 10K. Alright. Okay, we're at 400. $2K, 7, 10, 11, 13, 17, 20. No drop off. Looks good. Okay, so the transformers are figured out which tap to use, which wasn't the one that was advertised. That's why you run through these tests. What was the white ones allegedly for? Let me. Yellow was supposed to be for 8 ohms, and that is clearly incorrect. Let me disconnect these wires and turn this over and see what the white one was supposed to be for. White was for 2 ohms, green for 4, yellow 8, orange for 16. I'm using the 2 ohm tap. Hope I did this right. Okay. Well, going to build it that way. We'll see what happens. Turn off the equipment here. Enough for today. I'm going to get back to soldering, and I'll pick up sometime in the near future with another update. Cheers.